Alright, so welcome back to particle physics understanding model. This is lecture 28 and in the previous lecture we finally wrapped up spin half, right. Spin half representations in quantum field theory. We saw that spinors are nothing but yet another representation of the Lorentz group, probably the most important representation because that describes fermions. And then we saw that left handed fields and right handed fields live in their own independent representation, right. They are represented as Weil spinors or two component spinors, correct. And this is something that we saw by also breaking down the Dirac equation into the Dirac Lagrangian rather into two component spinors, and we saw that the kinetic terms came independently, right, as far as the left handed and right handed spinors are concerned, and it was only the mass term that put a left handed field paired with a right handed field and vice versa. And finally we got our first glimpse of some of the intricacies of the Standard Model, which is that in the case of in a theory where the fermion masses vanish, then the left handed and right handed Lagrangians can exist independently. You can have completely two different theories existing independently, and that is what we call a chiral theory. And we saw that the weak force indeed is a chiral theory, and this is why it is totally fine to charge just the left handed spinors under some force that you want, in this case the SU2 weak force, and leave the right handed spinors alone, and that is exactly what nature has done, and that is how we can understand why or how parity is violated maximally by the weak force. Okay, good. So we have dealt with various representations of Lorentz invariance. Okay, so that is indeed the first step to understanding what the Standard Model is made of. So we saw spin 0, half and 1, probably not in that order, but now we understand how to construct Lorentz invariant theories in quantum field theory, embed the correct degrees of freedom in the correct fields. Okay. Next we are going to deal with yet another symmetry, okay, that for reasons not completely understood that nature seems to really love, and that is gauge invariance. Okay. So it is worth saying now that there is a reason that we want our theories to be Lorentz invariant, right. We want everything to respect relativity, otherwise all hell will break loose, correct, because this is where you get notions of causality, locality and so on, right. You want to avoid all sorts of paradoxes like the grandfather paradox, telephone paradox and all that, right. So that is the reason why we cherish causality, and that is the reason why we want everything to be Lorentz invariant. We want physics to be the same in all inertial frames in flat space, correct. But gauge invariance is something else, right. We already had a taste for it. Remember, we wrote down the field strength tensor, right, when we dealt with spin 1. Remember this, and we saw that under a mu going to a mu plus any arbitrary function alpha x, partial mu of alpha x, we saw that this is invariant. The field strength tensor is invariant. So if you construct a Lagrangian using just the field strength tensors, it is invariant. So what is this? This is a redundancy in the description of the mediator field, correct. I can use this instead of this to describe my field basically, right. So what is so fundamental about that is not completely clear. Okay. There are many beautiful consequences that come out of this, but why should nature again and again make use of this symmetry in order to describe the world, right, in order to construct the fields making up the world is not completely clear. Okay. Nevertheless, it is there, you do have incredible consequences, there is a lot of geometric meaning to this, all of which we will not get into now. It all seems to be a nice self consistent jigsaw puzzle that all fits well, okay, but it does not arise out of something like causality, a need for causality or anything like that. Okay. It is just mathematical symmetry that that does get manifested, okay. And some people do not even like calling this a symmetry, because after all this is just redundancy in a field description, right. It is not like you are actually doing some transformation to a field like we saw in Lorentz transformations, rotations and boosts and so on, right. This is just a redundancy in field description that the Lagrangian seems to respect. Okay. Okay. So, with that introduction, let us see how we can construct gauge invariant theories. Okay. We find that the standard model not only respects Lorentz invariance, but also gauge invariance. So, might as well go ahead and understand gauge invariance. Okay. So, let me write down a Lagrangian that we already saw was gauge invariant. What is this? This is the Lagrangian of free photons, right. This is where you get the Maxwell equations from, right. Is this gauge invariant? Of course it is, I just wrote down f mu nu is gauge invariant. So, this is of course because I have 2 f mu nu's, I can call this doubly gauge invariant, absolutely gauge invariant under this gauge. Okay. Okay. The fun begins when you want to start adding other fields to this picture. Okay. For instance, if I want to add scalars, okay. So, I want to add complex scalars to this, okay, to gauge invariant theory. How can I do this? Remember, for a global charge, what do we mean by a global charge? When this is, when I can replace, where I can reface, right, all my fields with a phase that does not depend on the space time label, then that is a global charge, right. The field all over the place gets refaced by a single phase, right. And if a theory is invariant under that, then there is a global symmetry in the theory, correct. And of course, a theory can be invariant under that because we can write the mass term like this, which manifestly respects the symmetry. We can also write down the kinetic term this way, again it manifestly respects the symmetry, right. Okay. But necessarily gauge invariance means I cannot just do this, I need to have a local transformation. Okay. This is not a gauge invariant theory, okay, because I need to make sure that there is a field, there is a redundancy in the field description. Here if it is just 1 theta, it is not a redundancy in field description, right, it is just some refacing, correct. So, that means I need to look for, I am going to switch variables slightly, I need to look for a theory where the refacing happens locally at every point in space time. I need to pick up a different phase, okay. That is what gauge invariance means, okay. So, here also see the gauge actually was a function of the space time point itself, right, the space time label, okay. Now let us see, Let us again look at the mass term. Okay. Is this term gauge invariant? Yes, it is. Even though it is a local transformation, even though it is a local rephasing, it is still gauge invariant. Okay. Good. Then how about this? How about the kinetic term? That is not gauge invariant. How do you see that? You do the expansion, right, and you see that some of the phases cancel each other, but then I also have to differentiate with respect to alpha, correct? And then the alpha terms contain cross terms that do not actually go away. Okay. So, because of cross terms, this is not gauge invariant, the kinetic term. Alright. So, how do we proceed then if you do not have a gauge, if you do not have this term? The thing is, the strategy then is you have to find a way, okay, to combine the kinetic term of the phi field, okay, and the phi star also, actually phi and phi star fields, and this a mu field, okay. And notice that both of them transform non-trivially, right, under some gauge, right, under the gauge. So, we have to see if we can find a combination that gets rid of this alpha in the Lagrangian, okay. And I am going to show you how this arises, okay. And before I get there, let me slightly rephrase or redefine some of these things. I am going to say that instead of having this as the field redundancy, I am just going to slightly redefine that alpha, so that generically, okay, the redundancy that I am looking for is plus, I am going to add some constant to this 1 over E. You can see where this is going. What is that E? That E is exactly the coupling constant. It is not electric charge, it is the coupling constant, okay, of QED. So, that means what am I looking for over here? Well, this E is different, this is still the mathematics E exponent, right. Now, this is the transformation under which I want the theory to be invariant, and you will find that if I were to construct an object like this, okay, I am going to define this object as a combination of the 4 derivative and IE times A mu, okay. If I apply this transformation on this combination, okay, of the derivative and the field, then you will find, what do you find? That under the transformation, this goes as e power minus I alpha of that, okay. How do you see that? Take the partial derivative, sorry, take the the partial derivative of the 4 derivative basically on phi. I will have the usual dou mu phi, right, but then I will also get a term that looks like dou mu of alpha, correct, because I have to integrate that also, which I will multiply with the phi again, right. And then over here you see that over here you see there is another partial mu of alpha, right. So these two basically would cancel each other because you have the correct signs for I and all that. There will be a -1 picked up over here which will cancel the partial mu of alpha over there. Okay. So that is how that gets done, and you will end up with a refacing of this entire object. Okay. So I have been calling this an object, but the object has a name now, and I hope you will agree with the name. The name given to this is it is a covariant derivative. See, it is not really a derivative, it is a derivative plus a field. Nevertheless, we like to call this a derivative because this is ultimately what we are looking for, right. We wanted the kinetic term also to be invariant under the gauge transformations. So instead of writing that as the kinetic term, I can now use this as my new derivative, which is covariant. That is, just like Lorentz covariance, now you have gauge covariance, right. It transforms the way I want, it transforms the way the field transforms, basically the phi field transforms. Okay. Okay. Now you will agree that I can now write down the entire Lagrangian, okay, as, of course I have to start with the kinetic term for the photon, but now I think you will agree that I can also write a kinetic term for the scalar, and this is explicitly gauge invariant now, right, because this goes as e power minus alpha x, that goes as e power I alpha x under gauge transformations. And of course the mass term, which was not problematic to begin with, correct. What shall we call this theory? This is what is known as scalar QED. Is there any scalar QED in the real world? Of course there is, right. We do have charged scalar states, we have charged pions, right. In some beyond the standard model theories we have charged Higgs bosons and so on and so forth. Okay. That is the Lagrangian for scalar QED. Okay. Notice that something very interesting has happened. By requiring gauge invariance, I am now making the photon field and the scalar field interact with each other, right. So I will make a stronger statement about this as we do spinor QED also. Okay. But see, you did not have to put in the interaction just came out by demanding gauge invariance, right, and it has a very specific structure if you want gauge invariance, correct. In particular, remember again when we talked about Feynman diagrams, I said there were certain Lego blocks or building blocks that those are the only building blocks that you could use to construct Feynman diagrams, that is the interaction vertices, right. Now here you can see that this is totally allowed with two scalars and a photon. Why? Where does the term come from? Take the kinetic term. Okay. So I have one over here, I have one photon and one scalar, but then I hit it with another d mu phi. From there I can pull out another photon, correct. So two photons could hit the two derivatives, sorry, two phis could hit another derivative, or two phis could hit a photon. So this is totally allowed. Okay. But at the same time, what else is allowed? Two phis can also hit two photons, correct. You can see that, right, 1 2 and then I hit it with this, and then again you have A and phi. So this is also allowed, but clearly this is not allowed. Right? There is no way, the photon always comes with a phi. So that means if I have 2 photons, I will necessarily have 2 phis. Okay. So, but a phi does not always come with a photon, phi sometimes comes with the derivative also. That is why I can do this, but I can't do this. 2 photons will have to come with 2 phis, can't come with just 1 phi. Right? So now you can see where all the building blocks actually come from. Right? Good. Now I can generalize this to not having just one field. If I have multiple fields, okay, and then I call the fields phi 1, phi 2 and so on, okay, so that n labels the scalar field, then generically I can write down a Lagrangian with n different scalar fields, agreed. And another generalization I can do is the gauge transform could basically be for each of those fields labeled by n, I can have a different charge basically, right. One of them could have charge 1, another could have charge 370, another could have charge 5, etc., 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 or even fractional charges 0.0007 could be a charge. You are completely free to do that. Okay, we do not know how charge quantization really works. So right now you are completely free to do that, right. And how to write the covariant derivative? That would just mean I have partial mu plus I e q n a mu phi n. Okay. So this is where electric charge comes from. So never get confused with electric charge and this E. This E is just the coupling constant. Okay. The reason it is given the label E is that it reminds us of electron and all that, but then it's not part of the charge. The charge is just the Qn. Okay. Okay, good. This is where we get the notion of charge in QED. Okay, so how about spinor QED now? That is, now we want to add fermions to a theory of photons, to the free photons. So I think now you will agree that a lot of these things exactly go through. Again, I can take a spinor field, my gauge transformation is just this, and of course for the photon nothing changes, that is still the gauge transformation. Okay. Then how do I construct the covariant derivative? This means this is now my covariant derivative in exact analogy with scalar QED. That is my covariant derivative, which under the gauge transforms would go to e power minus alpha of x d mu of x, yet another gauge transformation, yet another rephasing, right. So then would you agree that this is the Lagrangian? You can start again with the kinetic term for the photons plus the Dirac Lagrangian, but now with a covariant derivative. Okay. Now this is where you get the rules for constructing interaction vertices in QED. Okay. So is this allowed? We already knew this was not allowed because spin angular momentum should be conserved, but now we see this from the point of view of gauge invariance also, right. Even gauge invariance doesn't give you this term. Why? Every time you have a photon, it always comes with the spinor field. So if I have 2 photons, I better have 2 spinor fields. Okay. So this is not allowed, whereas manifestly, well, not so manifestly, this is allowed, right. How is that? Because I can take one spinor field, I can have 2 spinor fields, one of them touches the derivative, the other touches a photon, in which case this is totally allowed, right. Yeah, okay, very good. Okay, so now here is yet another way to think about gauge invariance, okay, forcing all these interactions between scalar fields and spinor fields and the photons, right. The way to think about it is, originally we started with a photon field, knew that it already contained gauge invariance, and then we tried to force some extra interactions such that you can incorporate scalar fields and fermion fields, correct. But really the way to think about it, this is my favorite way of thinking about it, is you can start with a theory of electrons, okay, or a theory of charge scalars, okay. So start with electrons, you can always do that, right. You can write down a Dirac equation, and then you want to make it gauge invariant, okay. If you do that, you cannot help having, okay, a force carrier, you cannot help introducing the photon, okay. You cannot help introducing that in order to get the symmetry. In other words, if you want gauged forces, which is what we generally call fundamental forces, as opposed to say the pion mediating some force and all that, right. If you want gauge forces, then you necessarily have gauge mediators. See, when we motivated quantum field theory, we said this, right, that forces are necessarily mapped onto a particle state which acts as the force carrier or the mediator. This is where it comes from. All of this comes, especially for fundamental forces, this comes to you by demanding gauge invariance itself, okay. And also notice that the mediators have to be in massless, because in a Procol-Lagrangian, right, in the Procol-Lagrangian you had a mass term, right, for this, and remember this was not gauge invariant, not GI, right. But see, in real life, when we are talking about fundamental forces, we do talk about massless gauge bosons to begin with, okay. We will see that the W bosons, the Z boson, all of this in some form were actually massless to begin with, okay, and then mass came from symmetry breaking. So gauge invariance forced all of these things to be massless and also forced them into existence also, so that they could mediate these forces, mediate interactions between spinors and scalars, okay. This is one physical way to think about this, okay. So one more thing to notice here is that the photon couples to both left and right handed fields. How do I see that? From here, just from here, right. If you expand this, it does not distinguish between left handed and right handed, right. We already saw one expansion of this when we are writing the Dirac equation. Remember, from here we had this as the expansion for left and right handed. Now you will have these other terms involving photons that also give you interactions that couple equally to left and right handed. So, put differently, in other words, parity is respected, okay, by QED, just as we expect. This is exactly why electromagnetism respects parity in the form that we have, correct, without magnetic monopoles and stuff like that, right. Or said yet more differently, QED is a non-chiral theory, okay. See, all of this was handed to us by demanding gauge invariance, right. So, that is the beauty of this, it does describe nature amazingly, okay. So, I am going to wrap up this lecture by mentioning one important thing that could not have been written down from first principles in the Lagrangian here, okay. Nevertheless, that term is there, it is actually what is known as a dimension 5 term, that is why it was not obvious to have been written down here, okay. So, there is a missing term in the QED, in the the QED Lagrangian we just wrote down for spinors, okay. So, this is unique to spinors coupling to the photon, spinors coupling to the photon. Let me just break the suspense, let me just say this has to do with the magnetic dipole moment, okay, which also respects gauge invariance and Lorentz invariance. So, I am not going to write this down now, okay. It is a dimension 5 term, we are going to do only what are called renormalizable terms, the simplest terms, but of course I can refer you to Schwartz, where he shows how you can derive this term by taking the Klein-Gordon equation and the Dirac equation, square the Dirac equation, take the difference, and you will find that there is an extra term that you will get which cannot cannot help but exist, and you have to write it down in the full Lagrangian. And using, this is the term that gives a dipole moment to the neutron, magnetic dipole moment, so that you can control neutrons with magnetic beams and so on, okay. So, okay, I will leave you there, and then in the next class we will take gauge invariance further into non-abelian groups, and that is what is known as Yang-Mills theory, and we will proceed from there. All right, thank you, see you next time.